Hey, today we're going to talk about finding the area of an enclosed region in calculus. So you've got two functions and they trap a region, a specific region, and we're going to use our skills of integration to actually find the enclosed region. So we'll have an example here. This is the easier of the two examples because in this particular example we're going to take the top curve and subtract the bottom curve, and that's kind of intuitively easy to do compared to the other style where we're going to have to take the right curve and subtract the left curve. More to come. So let's take a look here at the example we have for you. We want to do this. So the scoop is we've got to find the area of the region enclosed by these two curves. The first curve is f of x equals x squared plus 2x plus 12, a parabola that just opens upward we're quite familiar with. The second curve, a line with a negative slope and a y-intercept of 3. That's g of x equals negative 4x plus 3. And this is the vertical line that coincides with the y-axis, the graph of x equals 0. So the picture we're looking at here gives us the three curves, and you can see that the three curves enclose a region here. Below the red curve and to the right of the blue curve and to the left of the vertical line is an enclosed region, dotted with yellow here. This is the region we're going to find the area of, and to do so we're going to integrate. So we've talked a lot about this infinitesimally thin rectangle that makes up part of the region, and that's what makes integration possible. This infinite number of rectangles, each with an infinitesimally small width. In this case of a dx, that's just a very small difference in x's. If you can envision here thousands, starting from left to right, of books that are bookshelved from left to right, and each of those spines of books is like a rectangle. When we sum up all those rectangles or integrate all those rectangles, we'll end up with the area of that yellow dotted region. So that's the master plan here in front of us. So we're going to integrate the top curve, which is the red curve, minus the bottom curve, which is the blue line with a slope of negative 4. And we're going to do that from an x value on the left to an x value on the right. We're specifically talking about the x value on the left of negative 1 and the x value on the right of 0. So notice, if we're differentiating with respect to x, we're stealing x coordinates of intersection. We're stealing the negative 1 and the 0, where the 5 to 9 are insignificant in this particular case. So again, differentiating from negative 1 to 0, the function top curve x squared plus 2x plus 10 minus the bottom curve negative 4x plus 5, and this will be dx. Well, the rest of the work here, you've really been down this road. We're going to subtract these two. I'm now combining like terms. Being careful now, you're subtracting that second quantity, so both of those signs are going to change in there. So I've got a positive 2x and a plus 4x is how I arrived at that 6x. I've got a positive 10 minus 5 gives me that positive 5 when I'm combining like terms. Now time to integrate by adding 1 to the exponent, dividing by the new exponent, and I get that scenario. I evaluated from negative 1 to 0. Further work, first plugging in the 0, of course, will make each of the three terms worth 0. Minus, that minus significant and important. This is where some students drop the ball. Make sure you have that entire quantity. And now I'm plugging in a negative 1 and getting negative 1/3 plus 3 minus 5. So, you know, on the AB exam, you'll have some problems like these that are very complicated, and you'll be able to use a calculator. Well, problem like this is, elementary enough where you ought to be able to get home without a calculator, and certainly not of level of difficulty where we wouldn't expect you to do so. So here we're talking about combining these three fractions, least common denominator of 3, getting upstairs a -1 for the first fraction, +9 for the second, a -15 for the third. Combining things upstairs and getting a -7/3 in parentheses, got to remember to take the opposite of that answer and getting +7/3 for an answer. So when the dust clears here, we have found the area of that enclosed region, that region enclosed by the 3 curves, and we've opted to go top curve minus the bottom curve and integrated with respect to dx. Upcoming example now, a little more difficult. We're not going to be able to go top curve minus bottom curve. We'll show you what causes that and why you've got to approach things a little differently. But that's the kind of the nuts and bolts for how to find the area of an enclosed region, and that skill is going to show itself as we move on in this unit with respect to volume. Stay tuned. Over and out.